talk is thanks to a little bit of serendipity. I guess that's how these things work sometimes. I was reading Technology Review, and in the alumni section, there was a half a page on Howie. I didn't recall from school, he was a few years behind me, but I read the article about him and about tornadoes. And what little I knew about tornadoes was from the 1996 Helen Hunt movie Twister. My daughter and son-in-law live in Indiana, and one of the people who worked for my son-in-law was killed in a tornado. So I have some sensitivity to the subject. So I contacted Howie and asked him whether or not he could give a talk, and he said he would be happy to. So I thought that was great. So he was raised in Boston, Miami Beach. He has degrees from MIT in electrical engineering and meteorology, and he's a professor in the School of Meteorology at the University of Oklahoma. So Howie, it's all yours.
Okay. Well, good morning, everyone. It's a pleasure to be here, at least virtually. And I wish I could see you all in person. Maybe someday I will see some of you. I'm going to talk about some of the research that my graduate students and I have been doing with tornadoes for the last 4 decades or more. If you have any questions, please just pipe right in. I can't cover everything about tornadoes and everything we've done in the short time that I have, but I'm going to try to give you a little bit of a flavor for some of the things that we've done, what some of the issues are, and what we're going to be doing in the future. You're looking, we've been doing for quite a while. This on the right, this is a mobile Doppler radar, and there's one of my students who's outstanding in his field. And there you see the tornado and the supercell in Southwest Kansas that we're probing. And I'll show you some of the radar data from this particular storm just a little bit. Okay, what do tornadoes do? They do tremendous damage. And this is one of the largest tornadoes that we've ever studied. This is the tornado that hit Moore, Oklahoma. Moore is right in between Oklahoma City and Norman in central Oklahoma. This is from 22 May 2013. And I flew up in a Discovery Channel and PBS sponsored helicopter flight over the damage. And I want you to be impressed by how extensive the damage is, but also how, in a sense, local it is. There's a 1, 2, 3, 4, 5 block area where most of the homes are just about completely destroyed. You can see how wide the path of this tornado is. And it came from this direction, from the southwest, moving up towards the northeast. At the edge of the tornado damage path, you can see how this house over here appears to be undamaged, completely undamaged, whereas the building next to it has its roof removed, and some of the other houses are totally demolished. You can see a very, very sharp gradient in the damage. And this might say something about the differences in the structural properties of the houses, but probably more it's due to the horizontal gradient and the wind speed. The wind speed over here, just a short distance away, is a lot weaker than the wind speed right in here. So that's something to be impressed by. This is what it looks like at ground zero, and these are panoramic pictures that I took. And you can see that it looks as if a bomb's gone off. There's nothing left. Everything is destroyed, things strewn around. This is absolutely horrible. People lose their lives if they don't seek shelter, and they lose almost everything they have. There was some poetic justice, and at the end of February, a tornado hit Norman. I'm up here in Boulder, Colorado on sabbatical, and sort of missed it. The tornado just missed my house by a few miles, but it did damage, not this bad, and no one was killed, fortunately. But tornadoes are just horrible experience to actually have. So what are the broad scientific questions, scientific motivation. One is, what's the source of vorticity? And for those of you who took, were at MIT and took, I think it was 1802, vorticity is just to curl the wind field, plain and simple, curl the wind field. So vorticity is a measure of the rotation of the air. So what is the source of rotation in tornadoes? Why do they sometimes form, but most often don't form? Why are some cyclonic and others anticyclonic? Cyclonic tornado is one which rotates in the same direction that the Earth is rotating about its axis. And an anticyclonic tornado is one which rotates in the opposite direction. So in the Northern Hemisphere, cyclonic tornadoes rotate in a counterclockwise manner. Sorry about the other phone ringing. And anticyclonic tornadoes rotate in a clockwise manner. So in the Northern Hemisphere, most tornadoes rotate in a counterclockwise manner, but occasionally we get some that rotate in a clockwise manner. And what's the detailed structure of the tornadoes? Where are the strongest wind speeds? Are they aloft? Are they at the ground? Does it vary? Does it matter? Are there vertical wind speeds? What are the vertical wind speeds? What are the horizontal wind speeds? At what level do tornadoes form, and how, if at all, do they propagate upward or downward? Do tornadoes begin high up in the storm and then build down? Do they begin at the ground and then build up? Do they form simultaneously from the ground up through the storm? What's going on? And finally, and this is more of a theoretical fluid dynamicist problem, which has very, very great applications. What happens when a vortex interacts with the ground? There's the rub. And this is the boundary layer phenomena, the boundary layer behavior of a tornado. If you have a vortex that is interacting with the ground, interesting things can happen. And these will affect the behavior of the tornado, where the strongest winds are, and so on. Now, there are three major techniques, methods for addressing these scientific problems. The first, which I have been doing, are just observations. And most of the observations that I have been doing, and my students, along with me, have involved using Doppler radars. Doppler radars, which we take out to the tornadoes themselves. Observations are great. They have their limitations, but they provide ground truth. A second technique is numerical simulations, usually idealized. These also include, or at least used to include, vortex chambers. We don't use vortex chambers anymore because we are able to simulate tornadoes very, very well, or at least we're able to simulate what happens when you have a vortex interacting with the ground very well. And the nice thing about an idealized numerical model is you can do a controlled experiment. You can control various parameters in the environment to see how that would affect the behavior of the tornado. In real life, of course, you can't do that. You go out and you take what you can get. A limitation of numerical models is that it's very difficult to simulate the parent storm which spawns the tornado and the tornado itself with good fidelity. And the reason for that is, in order to simulate a tornado, you need to have very fine grid spacing. Tornadoes tend to be in the order of several hundred meters across. They can be as large as several kilometers across. But ordinarily, the average tornado is only 200 or 300 meters across. To really simulate the tornado well, you need grid spacing of 10 meters at most. And in order to represent the small scale turbulent eddies, you need to get down to 1 meter or even less. And to do that for three-dimensional model, the computer capacity and so on right now is not quite up to that. We're down to the point where we can get down to 10 or 20 meters, but we're not down to the 1 meter or less. Finally, another technique that's used is to is to take observations and assimilate them into numerical models. And there's a whole branch of meteorology now which involves assimilating data into numerical models. And this is quite complicated. And by doing so, you make the numerical models reproduce what's actually out there. At least you try to do that. So this is for non-idealized experiments. So for example, we had a tornado in Norman at the end of February. We can take the observations, limited observations that we have, including radar observations, assimilate them into a numerical model and try to reproduce the tornado. We've actually, one of my colleagues here up in Boulder, the National Center of Atmospheric Research, has actually done this already, and we're going to be looking at this. Okay, moving on. Why do we need mobile Doppler radars? Why do we need mobile radars? There's a network of radars, the NexRad radars, also known as a WSR 88D, weather surveillance radars designed in 1988. They're getting to be a little bit old right now. The radar beam spreads out with distance from the radar, and the radars can be anywhere from right next to the tornado to 200 or 300 kilometers away. If you're far away from the radar, you don't have very good spatial resolution. You can't resolve the tornado. So we try to maximize the spatial resolution by getting really close to the tornado. When I say really close, I generally mean between 3 and 10 kilometers. If we're closer than 3 kilometers, then we're in danger from flying debris. You don't have to be in a tornado to be hit by flying debris. We once were collecting data in a tornado. We were probably 3 or 4 miles away. And after the tornado had passed, we drove down the road to see exactly what the damage was like. And we found that just a few miles down the road, there were telephone poles lying in the road. And this was not in the tornado. They had been flung out. So you don't want to get too close. On the other hand, you don't want to be too far away. If you're greater than about 10 or 15 kilometers, your spatial resolution is not quite as high as you would like. The resolution might be 100 meters, and we really need to be down into the tens of meters type resolution. Another thing is that we want to optimize the number of cases. If you wait for a storm to get really close to a fixed site ground-based radar, you're going to wait a long time. Maybe every so many years, you'll get something. But we go out and we get many or a number every year. Also, if you get really close, you can have simultaneous visual observations, and that turns out to be very valuable. You get to watch the cloud motions and get to compare what you see on radar to what you see actually in the cloud. Now, in recent years, we found that there's a need for what are known as rapid scan radars. Most radars scan relatively slowly. Mechanically scanning radars scan relatively slowly. And the radar network in the United States right now, the NexRad radar network, will scan a volume of a storm, takes roughly 4 or 5 minutes. And it turns out that tornadoes can form on timescales much less than that. And if you consider what the timescale of a tornado is, well, you can look at a video and you can see that things are changing every so many seconds. But from a theoretical standpoint, you can ask yourself, how long does it take a parcel of air to wrap around a tornado completely? And it's usually very short. It's in the order of 10 seconds or so. So the time scales of tornadoes are in the order of seconds. So you need to have a radar that scans an entire storm in the order of seconds, not in the order of minutes. Another issue is that Doppler radars measure the line of sight velocity. They measure the component of the wind along the side of the radar beam. And what you want to know is the full 3-dimensional wind. In order to get the full 3-dimensional wind, what you need to do is have 2 or more radars at different viewing angles scanning the storm. And from geometry and dynamical and kinematic constraints, you can actually get the three-dimensional velocity. Another thing is that you can track reflectivity elements in 2 dimensions if you have a rapid scan radar. There's a need for polarimetric radars. The radars that are in the network, in the WSR88D network, are all polarimetric. We have radar beams that are horizontal and radar beams that are vertical. And I won't go into too much detail here right now, but it turns out that the additional information that we get from the polarimetric Doppler radars are as follows. We can locate updrafts in the storm without actually measuring the vertical velocity. And I'll talk a little bit about that later, I hope. More importantly, we can identify the hydrometeor types using fuzzy logic algorithms, so we can better understand the cloud microphysics. What's inside of a storm? What's the radar looking at? Are we looking at large raindrops, small raindrops, hail, flying cows, birds, insects? We see all these things, and using polarimetric radars, we can distinguish among them. Now, it turns out that in a thunderstorm, rain, as you know, will fall out into unsaturated air and it will cool. Same thing happens to you when you step out of the shower or step out of the ocean on a relatively dry day. You cool off. This forms a pool of cold air at the surface, and it turns out that that is thought to be important to the dynamics of the formation of tornadoes. I'll talk a little bit about that more a little bit later. And finally, polarimetric radars allow us to locate the debris in tornadoes.
We have a question here.
What is ZDR? What's a ZDR column?
ZDR, I don't want to go into this in detail, but since you asked, ZDR is the differential reflectivity. It's proportional to the logarithm of the ratio of the horizontally received beam to that of the vertically polarized beam. Just to give you a little simple example, if you have large raindrops, when they fall, they flatten. And as they flatten, that means that the horizontal radar cross-section is greater than the vertical radar cross-section. So you will find that the ratio of horizontally polarized radiation to vertically polarized radiation is going to be relatively large. On the other hand, if we're looking at small raindrops, they don't flatten. And the ZDR, the ratio of vertical to horizontal, tends to be 1. And so the log of that is 0. So also hailstones tend to tumble and have no preferential orientation. They also tend to have low ZDR. So by looking at ZDR, we can distinguish between rain and hail, for example. It turns out that if you have a very, very strong updraft in a thunderstorm, that what happens is that you get raindrops are then lofted or brought up to high levels in the atmosphere so that they're way below freezing, and they freeze. Eventually they freeze, but before they freeze, they maintain their shape. And so if you see a vertical column where you have very high ZDR, that means you must have very strong updrafts lifting the rain up to very high heights in the storm. So we use that to locate strong updrafts in the storm.
Thank you.
Okay, now we find that debris is characterized by something called low rho HV, and rho HV is a normalized correlation between the horizontally and vertically polarized beams. So if we have a lot of randomness, tumbling and so on, we're going to have a low rho HV. If we don't, we have a very high rho HV. It turns out that low rho HV means that we probably have debris. And you can look at the Doppler radar, and this is really incredible because we've been able to do this only in the last 20 years. We first showed that this was possible back in the mid 2000s, but you can actually look and locate, and I'll show you in a minute, a region of lower OHV, and you can say there's probably debris there. And you don't need someone on the ground telling you there's a tornado. You can see the debris in the air. Okay. Moving on. Let me just show you a simple, this is an iPhone video I took. And this is in Kansas a couple of years ago. And you're going to see the formation of a tornado right before your eyes. You'll see those clouds that are rotating around. This is the mesocyclone. This lowered cloud base is called the wall cloud. There's a tail cloud in here. We're looking to the west. You can see all the storm chasers in this rural area of Kansas coming up to where we're located with our radar. And you will see that it spins around, and you can see these pieces of cloud material called scud that are rising. And we're looking for the formation of a tornado in here. And you will see that. Now we're starting to get, looks like a funnel cloud. There's a condensation funnel forming over here. And there's a small tornado forming here. The second one over here. And they're going to rotate around each other. This is what's known as a multiple vortex tornado. You can see how this is taking place only in the order of seconds. Very, very rapid. There's the tornado. You can see debris flying through the air. These little dots over here, pieces of debris, probably boards from a building that was just hit. And that's called the debris cloud of dust. Now you don't see a condensation funnel. There's one over here. You can see how rapidly things are changing. Oops, there's a secondary vortex in there near the ground. It's not over with. There's another one over here. Here comes a funnel cloud. Look at the complexity. Look at the complexity of what's happening. Rotation on several different scales. Sometimes it's hitting the ground, sometimes it's not. The tornado is on the ground right now, even though you don't see a condensation funnel. There's debris on the ground. You do not need to have a condensation funnel to have a tornado. Here's another video I took, boy, 10 years ago.
Here's a little suction vortex.
There's debris. Second one. Same thing in the order of seconds.
Yeah, it looks like it's speeding up.
That's one suction vortex. Another one. More over here. Notice how they're going up. The air's going up.
You ought to be getting great data now.
I apologize for not hitting a tripoded video, but it was too windy and it was raining outside.
Howard, can you talk louder?
These are all small tornadoes.
Yeah.
Lasting just a second.
It's going to be a big one.
That's the main funnel cloud here. Look,
And
there's
then
debris
we're gonna leave.
flying in the air.
Debris in the air. Oh my God.
How did you know to be there?
How did you know to be there?
What happened?
I'll tell you later. We were following the storm on radar.
Okay, we've got to go. I'm sorry. I think it's not safe anymore. We've got to go. Shut her down. You get a multiple vortex tornado.
This is a problem we always had. The tornado's coming right towards you. At what point do you get out of the way? Or how long can you stay and collect great data safely? And we're zoomed in right now. I'm zoomed in, so we're not as close as it appears to be.
Are we unleveled?
Yes.
Okay, so we can move?
Yes.
Yeah, I think we ought to. Yeah, Jana, you still collecting data? How far is it away? To how many?
Still about 9.
Okay, hang on just a little bit longer then.
We're 9 kilometers away. I don't start to panic
collecting.
until
Should I drive?
tornadoes get to
No.
3 or 4 kilometers. It's not moving very quickly.
Why don't we just go?
Here you see the tail cloud, the wall cloud, and the tornado. This is from a major tornado that hit Shawnee, Oklahoma. Okay, that's it. Someone asked the question, how do we know to be there? I get up, well, the day before, in fact, days in advance, we know whether or not the conditions for tornadoes are possible. The night before, we get a better idea when we look at the computer models. And on the morning of the possible event, we look not only at the computer models, but we also look at the actual data themselves. So in the morning, we look at the computer models, and there are a number of different computer models. There are global models. There are models that just include as their domain the United States and Canada, parts of Mexico. And then there are more recently, there are computer models that are regional. And the more local the model, the smaller the grid spacing. And the regional models are actually able to simulate storms themselves in a fairly crude way, but they're able to simulate them. And we look to see what the model is doing. The model is not perfect, but it gives us some information. We also look at the data, the Raywensons, which are the weather balloons that are sent up all over the world at various locations, usually spaced around 300 or 400 kilometers apart. There used to be one at Chatham. That was your New England sounding, and it's an embarrassment. But it turned out that the place from which that sounding was released, the building was falling into the ocean. And they moved it, and they have not replaced it yet. So you don't have a Raywenson in Eastern Massachusetts, which is pretty amazing. It's sad. There's one down in Long Island near New York, and there's one up in Portland, Maine, and there's one up in Burlington, Vermont. But there's a big hole in southeastern Massachusetts now. Anyway, we look at the soundings. They're released twice a day at 0 and 1200 UTC, used to be known as Greenwich time. And usually we leave late in the morning or early in the afternoon to head out to a location somewhere within 200 or 300 miles from Norman. And I can talk more about that later. But this is the ideal situation. No trees, very little for the tornado to hit. And there's our radar. And we're out there pretty much alone at this point. And this is the wall cloud, the tail cloud, and there is the tornado. And there's just a close-up of what the tornado looks like. All right, little theory. The formation of what's called the mesocyclone and the mesoanticyclone. This is the main areas of rotation in what's known as a supercell thunderstorm. Supercell thunderstorms are different from the ordinary garden variety thunderstorms, which you experience a lot of in New England, especially during the summer, in that they last for a long period of time and they rotate. Ordinary thunderstorms last only about 40 or 50 minutes. The air goes up, produces precipitation, precipitation falls out, and that's it. So one-shot wonder. Oftentimes you do get a sequence of these ordinary cell thunderstorms. These are called multi-cell thunderstorms. They produce some wind damage, maybe some hail, but generally the worst that they do is produce strong straight line surface winds and lightning and so on. Supercells rotate, and the updraft, instead of lasting for just 40, 50 minutes, can last for hours. And supercells contract for great distances, and they rotate. How do they rotate? Here's a storm which is released, which is started. You lift the air up, it becomes buoyant, and it rises. And suppose you have an environment in which you have, say, an easterly wind below and a westerly wind aloft. This is a situation where we have vertical wind shear. The wind vector changes with height. Now, in this particular simplified situation, where we have an east wind below and a west wind aloft, if we were to put a paddle wheel in this flow, whose axis is oriented from north to south or south to north, it's going to start to spin like this. So this is rotation, which is produced about a horizontal axis. This is vorticity, but it's horizontal vorticity. Tornadoes have vertical vorticity. What happens here is that this region where the air is rotating like this gets bent. It arches over like this. It gets lifted in the middle, but it doesn't get lifted off to the sides. And when that happens, what we're doing in effect is tilting rotation or vorticity about the horizontal onto the vertical. To the north, we produce an anticyclonic vortex, and to the south, we produce a cyclonic vortex. And it turns out that if we look at the equations of motion, the dynamics of these vortices, we find that what happens is that the vortices are pretty much in centrifugal balance. There's a pressure gradient force which acts towards the middle and a centrifugal force which acts outward, and they both balance each other. For those of you who went to MIT, this was in 801, Physics 1. And this works for both cyclonic vortices and anticyclonic vortices. And so there's relative low pressure. The low pressure is what makes the air always go here to the left or always here go to the right. And what happens is this tilting is maximized at mid altitudes. So we have low pressure up here, low pressure here, look down here, low pressure and low pressure. And there's a pressure gradient force, which is acting upward. What's a pressure gradient force? If you think of two people pushing against a door, if they both push with equal amounts of force per unit area or pressure, the door is not going to move. It's not going to experience any net force. But if one person's stronger than the other, then there's a pressure gradient. The pressure that one person is exerting and is going to be greater than that which the other person is exerting, the door is going to move, going to accelerate to one side. And that's what's happening here. You get a pressure gradient force acting upward. And what happens is that upward pressure gradient force produces a new cell, more condensation and more precipitation. But the precipitation doesn't fall back into the updraft the way it does in an ordinary cell. It goes somewhere else. Now, these mesocyclones and mesoanticyclones are detectable by Doppler radar. And many years ago, back in the early 1970s, when people first began to look at storms with Doppler radar, they noticed that when a tornado formed, it was preceded by this mesocyclone aloft. And so they thought that they could go ahead and use this to issue forecasts, short-term forecast. If the Doppler radar were to see a mesocyclone aloft, that might mean that within 10 or 15 minutes, there could be a tornado. Very, very nice, except that it turned out that maybe 20% or fewer of storms with mesocyclones actually go on to produce tornadoes. But this became the basis for the development of a national network of Doppler radars. There's more to it than just this, but this is the simplified version. But these vortices do not become the tornadoes. What becomes the tornadoes are low-level mesocyclones, which form in a completely different manner. This is what the shape of a supercell looks like on Doppler radar. Looks like this. And what happens is we have an updraft in here, a downdraft in here. This air is called a forward flank downdraft, and it's cool. This is the precipitation that falls out of the anvil of the storm into unsaturated air, and it cools, producing what we call a cold pool. We also get air which moves down or sinks in the clear air here. This is called the RFD, or rear flank downdraft. And this may have something to do with the weight of precipitation, but it's also dynamically produced. And I can't say very much about that right now, except to say that it's it's caused by the configuration of the wind field. And the wind comes down and hits the ground and produces something that looks like a cold front, except on a scale of a storm. And this produces what's called the rear flank gust front. show you pictures in a minute, I hope. Ambient warm air comes in, cool air in here. Now, what happens is that in this area where you have the cool air, the evaporatively cooled air, it's negatively buoyant. That's that vector acting downward. Outside the storm, we have neutral buoyancy. There's warm air. It will not become buoyant unless you lift it. So basically, there's no buoyancy out here. If we were to put a paddle wheel in this flow, what's going to happen? The air is going to accelerate down inside the storm, but not do any acceleration at all outside the storm. It's going to start to spin like this. Okay. And that spinning motion is horizontal vorticity. And if we have the air comes from the east, say, relative to the storm, it comes into the storm, and then it hits the updraft and it gets tilted upward. And lo and behold, there's a low-level mesocyclone. That is what can produce a tornado. The mesocyclone aloft is what's responsible for producing the supercell and keeping the storm alive for a long period of time. But the rotation actually comes from the low-level mesocyclone, which we believe is related to this cold pull. There's a Goldilocks thing going on here. If there's no cold pull, you're not going to produce a horizontal vortex, which can then be tilted into a low-level mesocyclone. If there's too much of a cold pull, the air rushes down, and this rear flank gush front will wrap all the way around and cut off the warm air from flowing into the storm. Okay, I'm running low on time right now, so I'm going to skip over this very lightly. Here's a brief history of our field operations with radars.
We have a question here. Going back to your previous slide, in which direction is the tornado moving as far as being on the ground? If you're looking from the ground, which direction is that tornado moving?
Yes. Generally speaking, in this case, the storm and the tornado will be moving from, say, southwest to northeast in this particular case.
Okay.
All right.
Thanks.
So what will happen is, and I think I'm going to mention this later, is that you're sitting up over here and you see an anvil coming towards you, and then you start to see some light rain, and then you start to get some heavy rain, and then the heavy rain starts to get mixed in with hail, and then the hail gets larger and larger, and pretty soon you have nothing but hail, and then boom, there's the tornado. So we started out back in the late 1980s with the Los Alamos National Laboratory portable CW FMCW solid state analog X-band, that's 3 centimeter wavelength Doppler radar. My late colleague Wes Unruh provided this. And we were able to, for the first time ever, measure wind speeds in tornadoes using a Doppler radar being really close up. Then in the early to mid 1990s, we began to use a University of Massachusetts and Amherst W-band 3 millimeter wavelength radar, very fine resolution, 0.18 degree beam. Whoops. This radar had a 5 degree beam. This is 0.18 degree beam. For comparison, the next red radars are about 1 degree. So this was, less than 0.2 of a degree. Very, very fine resolution. We used this for a number of years. A lot of my students did theses using this radar. These radars are great. These are the highest resolution peer into tornadoes we've ever had. But there are problems, and the problems are that W-band radars are susceptible to attenuation. The beam doesn't get very far. You have got to be very close to the tornado. If there's rain around the tornado, you can't see the tornado. The rain just attenuates the beam tremendously. And the other thing we discovered was if something happens to the radar and the tube, that it costs hundreds of thousands of dollars and a year or more to get a replacement. So at that time, these were not off-the-shelf pieces of equipment. Then in the early 2000s, we used the University of Massachusetts X-band polarimetric radar. This was one of the first polarimetric X-band mobile Doppler radars. Again, we looked at storms. Many of my students got to use them. In the mid-2000s, we began to use a radar which came from the Navy. This radar was a phased array electronically scanning radar that had been used aboard ships. At Raytheon, you probably are familiar with this. And it was modified. The signal processing was modified so that instead of looking at incoming missiles, it would look at distributed targets in a thunderstorm. And this radar was at the Naval Postgraduate School. And we used it, and we made the first mobile phased array rapid scan measurements in tornadoes. And some of the data that we got was just incredible. I may show you some of that later. Then the next major advance was in 2011. Andy Pasmani and Jim Mead from University of Massachusetts, but then a company in Amherst built what we called RAXPOL, or the Rapid Scan X-band polarimetric radar. So this is the first rapid scan polarimetric radar. It was not phased array. It was mechanically scanning. And we've been using this for over 10 years, and it's incredibly prolific. The number of good data sets we've gotten have been amazing. And the way it works is that it uses frequency hopping. Frequency hopping was not a new technique, but it was new and that it was applied to our radar. Mechanically scanning radar, if you try to scan it around at 2 degrees per second, you don't get enough independent samples to get a good signal, to get good data. So what you do is you frequency hop 10 or 11 times. You change the frequency enough so that each scan gives you independent samples, but the change in frequency is not so great that your antenna is mistuned. This worked, and I'll show you what some of that looks like. So let's go W-band radar, highest resolution ever in a tornado. Vertical cross-section of the radar reflectivity. So if there's colored, then that means there's clouds and rain. In the middle here where there's noise, that's the inside of the tornado. It's hollow. This is called the weak echo hole, or the weak echo column. You will notice that right near the ground, the weak echo hole doesn't come to the ground. Here's another one over here, and the weak echo hole does not come to the ground. And what happens is that your targets, your small raindrops that are spinning around the tornado are centrifuged radially outward. The air motion in a tornado is in centrifugal balance, cyclostrophic balance. The inward directed pressure gradient force is exactly counterbalanced by the outward directed centrifugal force. However, for raindrops, they're much more massive than air. Centrifugal force wins. So they get centrifuged out, leaving nothing in the middle. So that this is not like the eye of a hurricane. Eye of a hurricane is there because the air is sinking. The air might be sinking in here also, but the reason why you get the hole is that the precipitation particles are centrifuged radially outward. Near the ground, that's not the case. Near the ground, when you take a vortex and rub it against the ground, frictional drag is going to slow the wind down. The wind's going to go to zero directly at the ground. It has to, unless the chunks of ground are flying up in the air. So the centrifugal force is proportional to the square of the wind speed. So the centrifugal force decreases to almost zero, gets very, very small near the ground, but the pressure gradient force stays the same. So that means that the air converges towards the center of the tornado. And so the precipitation particles now come towards the center. Okay.
Oh, there we go.
Here's a picture of the actual when we first got it. It's spinning around at 180 degrees per second. We do get
Oh, there we
some
go.
steam smearing
That's
and
recording.
azimuth, but it turns out to be not too consequential. There were some signal
Oh, there we
processing
go.
techniques for getting rid of the
That's recording.
smearing, but we don't do that. Okay, here's an animation. The first tornado we got with the radar was a big one, an EF4 tornado. And these are
What does
image
EF4 mean?
EF4, the wind speeds are probably 90, 100 meters per second. Wind speeds are way over 200 miles an hour. A very strong.
It's a horizontal view, or are we looking down from the sky?
We're looking at a horizontal view. The radar is here. And we're looking off to the, we look to the southeast and to the east now. I'll replay this in a moment. This panel here represents the reflectivity given in dBz. This is the ZDR. This is the Doppler velocity. Reds mean going away, green mean coming toward you. And this is rho HV. This is the cross correlation coefficient. Let's come back over here. Here you see this is every 2 seconds. That's the hook echo with a tornado with a weak echo hole appearing sometimes. We're scanning so low that we don't always see a hole here. This is dry air wrapping in around the tornado. There were spiral bands going around the tornado. Forget the ZDR right now. Look at the Doppler velocity, flow away from the radar, the red, toward the radar, green. That's what's known as a tornado vortex signature. When the Doppler radar sees that, you know there's a strong vortex and possibly a tornado. However, this is an indication of debris. This is rho HV, and it turns out that it is much lower than the background. The background rho HV is close to 1, the red, greater than 9/10. These low values in here are debris. And you'll see spiral bands of debris, which are not dynamical instabilities like those in a spiral galaxy. These actually represent debris that's being centrifuged radially outward aloft, falling, and then coming in along narrow bands. There's another one there into the tornado. So here even if we didn't see a tornado, we're sure there is one because we see the debris corresponding to where the tornado vortex signature is. Any questions about this? I'm going through this really quickly. These markers here, I guess it's hard to see, but this is 4 kilometers and this is 8 kilometers. So the tornado is kind of our magic distance away of 3 to 4 kilometers for the whole time. We had a crew from PBS's NOVA with us in this day, and I don't think they knew what they were looking at because when this appeared on television, they never showed a picture of the tornado. I think they were looking in the wrong direction, which was amazing. Okay, here's an even better tornado. You may think El Reno is the tornado capital of Oklahoma. It's west of Oklahoma City, and this is with Raxpol, and there's an animation. This is not every 2 seconds. This is every probably 5 or 6 seconds, but there you see the hole, weak echo hole where the tornado is. And you will notice that it changes direction at the very end. It was moving from northwest to southeast, and then it started to come towards us. This is the horrific tornado where Tim Samaras and some other people got killed. They were trying to place a little probe in the path of the tornado, which they'd done many times before. And in this particular tornado, a secondary vortex came right towards them. They had no chance. We managed to get out of the way and stay far enough away that we were safe. Where the tornadoes begin? Do they begin at the ground? Do they begin aloft? Where do they begin? We compute a quantity delta V max. This is at the difference between the maximum outbounds and the maximum inbounds associated with the vortex signature. And that delta V max is a measure of the strength of the tornado. So if you see the winds blowing 40 meters per second away from the radar, and then 20 meters per second toward the radar, that would be a delta V of 60 meters per second. That's pretty strong. If delta V is greater than 40 meters per second, there's probably a tornado. In any event, this is a plot of the height above the ground in kilometers. And along the abscissa, I've plotted the delta V. And you can see that around 1 kilometer above the ground, there are these greens that start to appear. We're starting to get some relatively high delta Vs about 1 kilometer above the ground. This is the low-level mesocyclone. All of a sudden, with almost no warning, we jump to 80 meters per second right near the ground. That's the formation of the tornado. And we believe what happens is this low-level mesocyclone instigates the tornado at the surface. It then spreads upward rapidly. It shoots up to 2-3 kilometers. And in some instances, we've seen the indication of the tornado all the way to the top of the storm, up to 15 kilometers or more in height. And then the tornado really rages on. You can clearly see the tornado is strongest at the ground and weakens with height. This is a secondary vortex, delta V, a region of strong delta V, and we can track it. And my student tracked it all the way around. This is the mesocyclone. This secondary vortex wraps around the mesocyclone, and it moved at 78 meters per second. That's over 150 miles an hour. The people who were in the path of this had no chance. It was moving towards them at 150 miles an hour. The ground relative wind speed was 135 meters per second, which is 300 miles per hour, or EF5. That's as strong as tornadoes get. Strongest wind speeds, my group and another group have ever measured in a tornado are around 300 miles per hour. This is the multiple vortex tornado, a close-up from our Raxpol data, the separate weak echo hole for each multiple vortex, each with a separate vortex signature. You just look for the strong shear. This is spectrum width. Forget that. That's the spread of the Doppler velocities within the volume. But this is rho HV. This is the debris signature. And notice how it's scalloped on one side. Each of those scallops is associated with each separate vortex signature. So these are tornadoes within tornadoes, each producing their own separate debris signature. And these are horrifically dangerous. We were able to track these vortices. They seem to begin in the rear flank, tornadoes moving like this, the bottom left to the upper right, and they tend to dissipate in this region. They don't go around like horses in a merry-go-round. And this is because the storm is moving. Why do we get multiple vortex tornadoes? Numerical experiments have confirmed this. There's something called the swirl ratio, and that's a measure of the wind speed going around the tornado to the wind speed going straight up. And it's very complicated to try to understand why the swirl ratio is what it is. I'm not even going to try to explain it. I don't completely understand it. But if we have a low swirl ratio, we have a lot of upward motion at the beginning, at the center of the tornado. This is a vertical cross section of the radial component of the wind. As we increase the amount of swirl, the low pressure area near the ground becomes stronger and stronger, and we get a pressure gradient force that acts down. It sucks air down at the center of the tornado. If we increase the swirl ratio a little bit more, then that downdraft can make it all the way to the ground, and the vortex becomes very, very wide. When this happens, we get very strong lateral shear in the vortex, and we get little instabilities that form these smaller scale tornadoes within the major large tornado. We can actually look at an animation of the rotation in the storm by looking at the debris. This is the debris signature, and you can see the debris in the cyclonic tornado is spinning around in a cyclonic fashion. But look what's happening out over here. There's a little piece of debris here that's spinning around in the opposite direction. And it's also moving to the southeast. We can get these anticyclonic tornadoes in cyclonically rotating supercells. And this is what the major cause is of anticyclonic tornadoes. These do damage. They're usually not as strong as the cyclonic one. But the amazing thing is that we've been out there, and every time we've seen an anticyclonic tornado, we're clueless. We were watching the cyclonic tornado, and the anticyclonic tornado came up total by surprise. And in fact, in this particular day, it came right over us, came right overhead. And fortunately, it was so weak that all that happened was vegetation was flying in the air. But that's the cyclonic tornado. And you can see it has the weak echo hole. It develops. Here along the rear flank gust front, along this end, you start to see stuff spinning in the opposite direction. And that turns out to be the anticyclonic tornado. The cyclonic tornado vortex, flow away, flow towards, and over here, it's flow away and flow towards anticyclonically. Looking straight up, that's what the radar echo looked like, straight up. It's the mirror image of the cyclonic tornado. That's looking straight up at the cloud, and it's a mirror image of the cyclonic tornado. We're looking up in this direction. Red is flow away, green is flow towards. That's an anticyclone. And then here's the debris signature. Okay. I'll skip that. We also see things called satellite tornadoes. There is a major tornado with a weak echo hole, but a second tornado forms up in this location, as denoted by that hole. And I don't have time to show you the Doppler wind field. Trust me, there is another tornado there. And you can see that it rotates around the main tornado. And that's different from a secondary vortex. This is actually another tornado that's weaker than an adjacent tornado, and it rotates around it. Another thing that we can look at is the debris signature visualized in 3 dimensions by looking at the isosurface of 0.8 correlation coefficient. If the correlation coefficient is 0.91, we're not looking at debris. If it's below 0.8, we're probably looking at debris. So there's the isosurface, and you can see that, it is a column, but it's broader near the ground. And here you see the debris signature start to disappear aloft. The tornado is dissipating, but near the ground, we still see the debris signature. And what this tells us is that when the tornado dissipates, the upper part gets narrower, but the bottom part, the debris signature widens. So when you're looking at a Doppler radar, you see the debris signature getting wider and wider. You might think that, oh my, the tornado is getting bigger and bigger. It's actually the opposite. It probably means that the tornado is dissipating. So you need to look both at the tornado vortex signature and the isosurface of ρHV. I'm seeing there are a bunch of comments on chat. If you give me a second over here, I can pause and, well, it's not showing it. Okay, here we go. Okay, I better look at these a little bit later so I can finish my talk first. Okay. Okay, I'm almost done. One of the things that we're doing right now is we're looking at polarmetric spectral densities. I don't have too much time to talk about this, but ordinarily we look at a measurement of the, say, the reflectivity. That's the reflectivity, or the ZDR. It turns out that if we slow the radar down, we can actually store the raw data and calculate the spectra of all the polarimetric variables. And this is a case when we're looking up at the top of a thunderstorm, and we're seeing a bimodal spectra. So at 13.5 kilometers range, which is up in here near the top of the storm, we're noticing that we have high reflectivities have this, say, 10 meters per second velocity, and we have Up here, very high velocities, maybe 25 meters per second at high Z. But in this region in here, say 15 meters per second, we have relatively low relative reflectivities. That tells us that we have two different types of particles, which is very interesting because now we're able to get, say, something not only about the type of hydrometeor that's there, but something about the spectral properties. I'm going to skip over some of this stuff, not important. Let me just get to the future because I've gone here an hour. Future radar that is being finished right now. The radar is actually built, but the software hasn't been completed. This is called the polarmetric atmospheric imaging radar. This is a radar which uses the imaging technique, a fan beam or a relatively wide elliptically shaped beam illuminates a vertical swath of the storm, but electronically directs the beam for reception. So it's like taking a flash bulb, illuminating the storm, and then electronically using phased array technology, direct the beam to different parts of the storm. And this can be done almost instantaneously. I'm going to skip over some of this. One of the nice things about spectral polarimetry that I just mentioned is that we can separate debris from air motion. And in a tornado, what we look at are the small raindrops. But if you have debris in the tornado, it gets centrifuged radially outward. That's a problem. If you want to find out what the actual air motion is in a tornado, the debris is not moving with the air. You need to separate them. We're hoping that spectral polarimetry will allow us to do that. We actually, one thing one can do is use a mobile Doppler radar. We tried that once, and it turned out the range of the LiDAR was supposed to be between 5 and 10 kilometers. But whenever there was a tornado, the tornado was always beyond about 5 kilometers, and the radar couldn't see, the LiDAR couldn't see beyond that. Earlier that we used the radar to look at snowstorms. This is just a video I took of the radar scanning. We're at Plymouth Harbor last year. Winds gusting is over 70 miles an hour, and that's quite an experience, but I don't have time to talk about it too much unless you ask specific questions. A shameless plug is that my next book out on clouds, which is going to contain some of what I talked about in today's presentation. It's at Oxford University Press, and it's being worked on by them right now. It's being produced. So with that, I think I'm going to stop. And what should I do now? Should I stop sharing?
Yeah, I think you should stop sharing, and there are a number of people with their hands raised.
Okay. All right, I'm going to start from the beginning over here. It's flickering around here. My chat is flickering. How can I get it not to flicker? There we go. Okay, that's a Bob Primack. He watched a tornado overhead. Wow, great. The National Security relied on actual observations call a warning. Seemed quite a bit based on radar. Right. Back in the olden days, in the very olden days, people would see a tornado, report it to the National Weather Service, and the warnings were based on that. Then in the 1950s, people began to use radar. They looked at the hook echoes and used those as an indicator of a possible tornado. Then in the beginning in the late 1970s, with Doppler radars, they began to look at mesocyclone signatures, but the operational radars didn't come into being until the early 1990s. A radar warning right now is based on the tornado vortex signature. That's the shear, the outbound next to the inbound Doppler velocities, and the polarimetric debris signature. That's what the radar warnings are based on. Visual observations, though, are...
Before you get past that, are the warnings fast enough to be truly useful to the potentially affected folk?
Most of the time, yes. Not always, but most of the time, yes. usually you can see the TVS 10 or 15 minutes before the tornado actually forms. So from that standpoint, people can be given 10 or 15 minutes notice. What's even better than that is that the supercell that spawns the tornado can be detected by radar a long time before that, maybe a half an hour in advance. And what the Weather Service can do is tell you that there's a storm which is kind of heading towards you. They'll issue a severe thunderstorm warning, and they'll mention that severe thunderstorms may produce tornadoes with little to no warning. The Norman tornado was a perfect example where the warnings were good. The storm was detectable 10, 15 minutes in advance, and the warnings went out. But sometimes the tornadoes can form very, very quickly, and they may not be warned. But most of the time they are warned. Does that answer your question? It depends. If you're given a 10 or 15 minute warning, what you do based on that warning is important. If you seek shelter immediately, that's great. If you ignore it, that's not great. If you get in your car and try to outrun the tornado, well, if you know exactly where the tornado is and how it's moving, then you can drive and get out of the way. If everyone does this at the same time, there's a traffic jam. And I was once in a traffic jam when a tornado was coming towards Oklahoma City, and we got into a traffic jam and couldn't move. And that's another long story, but the best thing to do is seek shelter in your house, or if you have 10 or 15 minutes and in 5 minutes you can get to a shelter, then you need to get to your shelter.
Last summer, there was a prediction that there would be some tornadic activities right along the Cape area. There was actually, I think, a tornado that, I don't know if it touched the ground or not, but it was right on Long Island. Then this cell moved across, ran over the vineyard actually, and then headed towards the Cape. And the basic behavior then produced a water spout as it crossed from the vineyard to the Cape, and it came ashore on the Cape. And we were watching it, switching back and forth between several different channels that were broadcasting live. And one of the channels, people had a mobile Doppler radar that is owned by the New England Cable Network and NBC consortium, basically, and they drove it down. It normally, a lot of times, it sits up at Worcester Airport.
Ted, is there a question here?
Yeah,
I'd like to move because there's a number of other people who have questions.
No, I just wanted to get this. So they showed back and forth the polarmetric data from that radar. The other people didn't have that. They had only the radar availability from the National Weather Service. And they weren't showing polarmetric, but they were showing Doppler. And it turned out that one of them sort of over predicted the warnings, in the sense that the tornado did touch down on the Cape, but it was overly warned, I think.
Ted, you have 30 seconds more, please. We really have other people who have questions.
Yeah, so I'm just trying to get across that I think that the radar warnings still are a little sometimes excessive. And I just wondered if Professor Bluestein would have a comment about that.
Yeah, it's always better to overwarn than it is to underwarn. And the radar warnings aren't perfect. If the radar sees a tornado vortex signature and has an indication of debris, there's a extremely high likelihood there is a tornado. If the storm has a tornado vortex signature and it's moving towards a certain area, then the Weather Service will issue a tornado warning, whether there is or isn't a tornado, because there is a likelihood that there will be one, and they know exactly where it will be if it happens. It's far better to tell people that you might get a tornado, take precaution, and then it actually doesn't happen, than to not warn at all.
Harry, you have a question?
Yeah, I heard last night on NBC News when they were talking about the tornadoes in Alabama, Mississippi, that there's some evidence that Tornado Alley is moving to the east, and they said it was due to global warming. And I was just curious as to what your view of all of that is.
Okay, this is a topic in its own right, and I could talk for about an hour on that. That's a very good question, and the media has been besieging me and other people about this. There was a recent paper that in which the authors showed that in the past decade or so, that there have been more tornadoes reported off in the southeastern part of the United States and fewer reported in the central portion of the United States. This could be a statistical fluke. There are decadal-long shifts in this. Also, let's see. So that possibly, it's probably real. Is that due to global warming? Here's where things get very, very complicated. In order to produce a tornado, you need to have a supercell. Now, there are tornadoes that don't come from supercells, but to get a big tornado, you need a supercell. And the conditions that are responsible for producing supercells are the potential for strong buoyant updrafts. This is determined by a quantity called the convective available potential energy. You think of this as the potential buoyancy in the atmosphere. This is related to how strong the temperature decreases with height. And you have to have a lot of moisture at the surface. One ingredient. Second ingredient is vertical wind shear. Strong vertical wind shear favors supercells. The wind shear is too weak, you don't get supercells. Okay, what happens in a warmed global warming scenario? Numerical simulations have been done, which shows that if you increase the low level temperature, that the Cape will overall increase, okay? But where the Cape is large, it's going to may shift around from one region to another. It turns out that some people have found that it depends on where you have wet soil adjacent to dry soil. Right now, we have in the central part of the country, a very dry land in western Kansas and West Texas and western Oklahoma, and it's very moist in eastern Oklahoma and eastern Kansas and so on. If that shifts around, that's going to affect the distribution of Cape. What about vertical wind shear? In the global warming scenario, the temperatures at the poles are getting warmer. The temperatures at the equator are not. That's resulting in a reduction in the pole to equator temperature gradient. It turns out that the intensity of the jet stream is related to the pole to equator temperature gradient. So if the pole to temperature gradient weakens, the jet stream is going to weaken. The jet stream weakens, the vertical wind shear is going to weaken. That's bad for supercells.
Now, there are two people in chat who've asked whether or not there are mitigating abilities to do anything about tornadoes.
I sort of laugh. I've very often gotten letters from people or emails from people saying, why don't you bomb a tornado or bomb a storm, and you can get rid of the energy and so on and so forth. And the obvious answer to that is when you do that, the bomb may do more destruction than the tornado itself. Right now, as far as I know, that there are no known sane, reasonable proposals for getting rid of tornadoes. You would have to get rid of the storms that produce them, and that would just be nearly impossible. And you would probably cause more damage to the ecosystem than you would had you just let an occasional tornado happen here and there.
As a
The,
follow-up to that,
question-
since if I might, has there been consideration to using something like microwaves, like in a microwave oven where it excites the water to heat it up? Could something like that aimed at the sky now, not affecting the ground, be used to heat up the water in or around a tornado to lessen its effect?
No, I don't. I mean, if you were to go ahead and irradiate a tornado, and you might make it stronger because you would be contributing to. If you irradiated the lower portion of the storm, you'd make the air more buoyant. And there are theoretical. If you consider where does the energy from a tornado come from, it ultimately comes from the buoyancy. How much warmer is the air than that of the surroundings? In fact, it goes as a square root of twice the amount of convective available potential energy. So if you heat the bottom part of the storm, you're going to make it worse.
I had another question
Sure.
that I posted. I hear about tornadoes in the United States quite a bit. I'm wondering, is there any other place on the planet where they have tornadoes?
Yeah, tornadoes occur all over the globe. And in fact, there are tornadoes in Canada, there are tornadoes in Europe, particularly in Germany and Italy and Croatia and so on, that part of the Mediterranean. Spain and England, UK has had a number of tornadoes, the Netherlands. China has had tornadoes, but not nearly as many as you would think they would have. Japan, Australia gets tornadoes, and South Africa gets tornadoes. But the United States, the central part of the United States, has the highest frequency of tornadoes in the world. And the reason for that is that we have the Gulf of Mexico. We're located in a latitude belt where we get storms moving from west to east. The jet stream is relatively strong. And we have the Rocky Mountains, which produce a region east of which there's relatively dry land next to moisture land off to the east. You can look around the world and find that these things, the situation occurs in a much more muted fashion than other parts. Also, I didn't mention Argentina and Brazil. South parts of South America do get tornadoes too. So tornadoes can happen anywhere around the globe. I must say that in recent years, because of Doppler radars, because so many people have gone out storm chasing, because of all the interest in the media of tornadoes, that tornadoes are now occurring or being reported at a much higher frequency in some locations than they were before. There's a heightened awareness. And there's the internet.
What about Russia? What about Russia?
Russia gets tornadoes too.
Yeah, I would have thought the steppes somehow would be really great with the
Yeah,
Euro.
I know very little about their climatology, but I am aware that Russia has had a number of tornadoes. Yes.
Are there other, I mean, we think of the tornado belt as where all the expertise is. Are there other places in the world that have devoted as much time as we have?
I think that in other parts of the world, the tornado forecasts are handled by the local weather service offices. In Europe, there's something called the European Severe Storms Lab, which really is a consortium of different groups within Europe. But I don't know of any other place in the world that has a storm prediction center like the one we have in the United States, which is responsible for predicting severe weather across the entire state. However, the local weather service forecast offices are responsible for the warnings. So in other parts of the world, in general, they don't have these centralized locations for the overall forecasts, but they do have the local forecast offices which issue the local warnings and so on. Does that answer your question?
Are we seeing more tornadoes at night than during the day now, rather than say 30, 40 years ago, or is that staying about the same?
I don't know the statistics for that. Most of the tornadoes occur late in the afternoon or during the early evening. There are tornadoes that occur overnight, and the tornadoes that occur overnight in general are not from supercells, because the supercells tend to be strongest during the heat of the day, late in the afternoon or early evening. There's another type of a tornado, which I didn't talk about at all. And this type of tornado was associated with what are known as quasi-linear convective systems. You probably heard the expression squall line, probably more familiar with that. And squall lines late at night during the latter part of their life can produce vortices, which do become tornadoes. They're usually not as strong as supercell tornadoes, and they tend to occur later on at night. There's a project going on right now that I'm not part of called PERILS, PERILS, and I don't know what the acronym stands for, but they're trying to study these nocturnal thunderstorms that tend to occur in the southeastern part of the United States at night. I have experienced these in Oklahoma, and they've occurred early in the morning, 7 in the morning, not when you would expect to find a tornado. And of course, they're particularly dangerous because people are sleeping at night and they're not aware, they're not watching the media, and so on. Have there been more of these? I really don't know. I would probably guess not. People are just becoming more aware of them. They tend to be more frequent in areas east of Oklahoma, Arkansas, Mississippi, Alabama, Tennessee, but they do occur everywhere.
Can you comment on the differences in terms of damage from straight line winds, microbursts, and particularly the low Fuchida number tornadoes?
Sure. Microbursts may produce wind speeds of 100 miles per hour, maybe 120 miles per hour. And that can produce extensive damage. An EF0 tornado can produce wind speeds of 70, 80, 90 miles per hour, and they're comparable. However, the stronger tornadoes are much stronger than 120 miles per hour, and the stress on buildings goes as the squares of the wind speed. So once you start to get to the higher wind speeds in tornadoes, you can do a lot more.
Is there gradient dependence on the damage? I mean, the fact that these other phenomena tend to be broader in terms of their scope of exposure, so that you don't get these sharp gradients in wind speeds.
Sure. Well, microbursts can be very narrow. They can be as narrow as tornadoes. Mm-hmm. But in large mesoscale convective systems, there were things called derechos, which are basically the conglomeration of the microbursts. And sometimes you can get 100-kilometer wide swath of very high winds that will obviously do damage over a very, very broad area, whereas a tornado will only affect a swath several kilometers across.
I don't mean to minimize tornadoes at all, but it seems that the ones that at least you've shown hit an area of ground that's relatively small compared to what, say, hurricanes do when they come in and can affect thousands of square miles of territory.
Yeah, hurricanes, clearly I study tornadoes. They're my favorite, but hurricanes can do a lot more damage. You can get wind speeds which are as strong as an EF3 tornado, and they can be over a much broader area. And tornado and hurricanes, as you know, can stop. They can sit in one place.
Yeah, right.
They can stall. And so instead of experiencing this big wind for 20 seconds or 2 minutes, it's for hours. So I think overall tropical cyclones are integrated over area and damage are worse than tornadoes. But having said that, you don't get 300-mile-per-hour winds in tropical cyclones, at least not yet. That might happen someday as the globe warms up, but also you get a storm surge in a hurricane, which is something you don't have to worry about in a tornado.
Well, Howard, you proved one thing to me is years ago when I went to South Africa, I had relatives down there, and I was at the airport and I was talking to this man. He happened to be the weatherman for the airport. And we were talking about high pressure and low pressure. I says, I came down here because I'm a retired engineer and I wanted to see if the vectors reversed on the other side of the equator. So I'll be damned, he didn't realize it. So he went back to his office and looked about the high pressure and low pressure, because for us, a high pressure is nice weather. For him, a high pressure is lousy.
Well, actually, I have to correct you there.
Yeah.
I think there's a misunderstanding. Low pressure is still bad weather. And
Oh, right. Oh, it's bad weather. Yeah.
But it's the direction that the wind rotates around high and low pressure systems.
Yeah, that changes, right.
Is reversed. So in the northern hemisphere, a low pressure area where you get the cyclone, and that's the storm. In the southern hemisphere, the low pressure area is an anticyclone, and the air is rotating in a clockwise manner.
I have to make a funny comment on that. My wife and I went to Australia about 20 years ago, and the very first thing she did was fill the bathtub and watch which way the water went down.
Oh, I did the same thing.
Yeah, that's an old.
I didn't in the sink.
Now that's an old myth, and the problem is your bathtub has to be perfectly level, perfectly smooth, and the drain has to be perfectly symmetrical. Otherwise, you're not going to see the effect. The Coriolis force is very, very, very weak. And for atmospheric systems that are what we call synoptic scale, that are thousands of kilometers across, that last for days, the Coriolis force is important. But for water going down the drain in your bathtub, it's been shown that it's not going to matter.
The first sports program with Guy Manila in the 70s, there was a discussion for about 2 weeks on whether or not athletes who run around a track clockwise or counterclockwise do it in that particular direction because of those forces.
I remember hearing about that too. Has no effect.
Bob Primack has a question.
Yes, about the southern hemisphere. Do tornadoes rotate the same direction in the southern hemisphere, or are they opposite?
It's exactly the opposite of what we have in the northern hemisphere. In the northern hemisphere, most tornadoes rotate in a counterclockwise manner, and there are a few that rotate in a clockwise manner. In the southern hemisphere, it's the exact opposite.
One follow-up, I don't know if you know anything about this one, but the Plainfield tornado in 1990, at the time, there was some question whether or not that was anticyclonic. Was it?
I remember that well, and I honestly don't remember whether or not it was cyclonic or anticyclonic, except that based on the analyses that I think that I saw, it was cyclonic.
Oh, because it was known that it came from an unusual direction, northwest to southeast.
Right, that's not okay. Now, most tornadoes go from southwest to northeast. There were some that go from west to east, and some that go northwest to southeast.
Okay.
In Illinois during the summertime, your prevailing wind aloft when you get storms is from the west-northwest.
Yeah.
And so that if you get storms that form, will tend to move towards the southeast, the tornadoes will move towards the southeast. So that is not unusual for the tornadoes.
So that's storm movement.
Right.
So it has nothing to do with which direction it was rotating.
No. No.
Can I follow up on Bob's question? If you have a tornado that's rotating counterclockwise in the northern hemisphere, has there ever been a case where it has crossed into the southern hemisphere, and what would happen, or vice versa?
Well, that's a great question. And the answer to that is, I will bet you money that there has never been a tornado right at the equator. Let's put it this way. In order to have strong vertical wind shear, that's associated with a strong horizontal temperature gradient and a reasonably strong Coriolis force. So you would have to be at a relatively high latitude. If a tornado crossed the equator, I would argue that the thing that caused the tornado was buoyancy, strong updraft, which was acting on pre-existing vertical rotation. This is be a non-supercell tornado, and these occur a lot in the Denver area, and I've seen them before. These are tornadoes in which the tornado often forms before there's even rain in the storm, and when the rain forms, the tornado disappears. In the case of a non-supercell tornado, the source of rotation is usually shear zone at the surface. Therefore, the Coriolis force, which is 0 at the equator, and would be infinitesimal just north or south of the equator, has absolutely no effect at all on the sense of rotation in the tornado. If you were to get a tornado at the equator, it's just as likely to be cyclonic as anticyclonic. And if it crossed the equator, the Coriolis force would not affect it at all. I don't think so.
Thank you.
I don't know of a tornado ever hitting exactly at the equator, but I imagine that if it did, it would, the physics would not depend on the Coriolis force at all.
Okay, Ted has a question.
Yeah, can you comment on these tornadoes that are spawned or triggered by, well, at least tropical storms, if not hurricanes?
I was expecting a question like that.
There was a particularly bizarre event when I was in graduate school or when I was on the research staff at University of Texas in Austin. People expected a landfall, and I don't remember if it was still a hurricane. I think it probably was, down in the Corpus area, and they flew their planes to Austin, Texas, and parked them at the old Dishfalk, not Dishfalk, that was the baseball stadium. In any event, the old airport at Austin, and tornadoes were spawned by that event, and one of those tornadoes landed right on top of the hangar where these private planes from Corpus had, and the thing never hit Corpus, but the tornadoes hit in Austin, which is quite a distance away from Corpus.
Okay, Ted, let him answer the question.
Yeah,
please.
so that's the question. There seems to be a spatial disconnect there.
Tornadoes often occur in mini supercells that occur in the northeast quadrant of landfalling tropical cyclones. It turns out that in the northeast sector of tropical cyclones, there's very strong vertical wind shear and low-level buoyancy. Numerical model experiments and observations have shown that the tornadoes form in what look like supercells, but they're not as tall as the supercells that we see over the continent. They're associated with vertical wind shear that tends to be associated with the surface friction, very, very strong winds coming in at low levels over the tropical cyclone. And these occur in the outer rain bands of the tropical cyclone, so they're not anywhere near the eye wall.
Well,
they're understood. They're understood. You can't predict them very well, but I think that they're understood why they're there.
Well, we've reached 11:30, And Howard, I want to thank you very much for a fascinating talk. I've certainly learned a lot.
Okay, great. I can hear the applause outside.
That was excellent.
Thank
One
you.
last question, if I may. How much accuracy was there in that Helen Hunt movie from years ago? Twister.
Not much. Not much. I remember that they have people are invited into someone's house for dinner before they go out and see the tornado. And that's never happened to us. We once got invited over to someone's house the day after the tornado, which was very nice. We were out in a portion of West Texas, and we were on these people's property filming the tornado, and they were invited us back the next day for lunch. That was a nice experience. There are no bad guys and good guys out there. And I've never seen a flying cow before.
That's good.
However,
John,
there has been, the movie has in fact affected research in both ways. For example, the device called Dorothy, if you remember, they put a device called Dorothy out. Well, that was a device that we used in the early 1980s, and we called it Toto, after Dorothy's dog in The Wizard of Oz. They took Toto and turned it into Dorothy. So there's a case where that was realistic. On the other hand, they also released these little instruments that became airborne inside the storm. And some people are doing that right now. They're putting in these biodegradable things that have GPS that will measure temperature and pressure and radio them back. You release them from the ground, they go up into the storm, provide observations within the storm. That was inspired by the movie. So
I thank you very much. This was very informative.
a pleasure meeting with all of you.